equation. Still, you make it non-exact to exact and then use integrating factor. And Bernoulli, you reduce Bernoulli into linear and solve your linear equation using integrating factor. And after that, we study Laplace in detail. Laplace methodology is very useful for solving second order, third order, first order, constant coefficient, non-homogeneous differential equation. Before that, second order differential equation, first order non-homogeneous part, we still use undetermined coefficient method, also consider analytical method. And then the famous method using Wronskian method, also consider analytical method. That is the first part. The first 1 to 3 chapters is about write down, yeah, analytical methods. And then next, chapter 4 and 5, we call it numerical method. So why numerical method? The reason is some of the engineering problems, science and technology, other fields such as business, finance, economics, even management, social science. There are problems very hard to solve by using analytical method. So therefore, problems such as highly nonlinear. Nonlinear meaning you cannot model. This is something to do with modeling as well. You cannot model a system, engineering system, any engineering, mechanical engineering, particularly yours, cannot be modeled in a linear differential equation. Either constant coefficient, homogeneous, or other types of differential equation, modeling, yeah. So sometimes experimentally, you will get non-linear models. So the numerical method is very suitable to apply to solve highly non-linear complicated problems. We use the word complexity, highly complex problems. So that's why you want to study these numerical methods. Basically, we are solving differential equation. We will start with the first order, and then you can move on to second order and third order. So at the moment, we will focus on the first order ordinary differential equation. And it is not easy as well to use numerical method to solve any higher order differential equation. It's not easy. So here we build up the foundation first. We try to solve the first order differential equation by using 4.1 is the Euler method, or you say Euler, some say is Euler. And then Hume's method, 4.2, and 4.3, fourth order Runge-Kutta or Runge-Kutta method. So all these methods are very important. It can give you a strong foundation, but there are thousands of methods in numerical analysis by the course by itself. We call it numerical analysis, or even numerical methods or computational methods. So many names are there. All these are now we can use computer softwares, calculators. Basically, at the moment, we need calculators. That is very, very important because it involves a lot of tedious calculations. It's not very hard. The only thing is time consuming. but you can use programming skill later on, yeah, for the research purpose, for the projects, for the journal publications, and so on. We have sophisticated softwares, tools, and then programming methodologies. Then you can embark on that later on, yeah, not at the moment. At the moment, we have to do it manually by calculation. At most, you can use calculator to shorten the time of calculations. Okay, so at the moment, we just focus on Euler method first, yeah. So today, we just go through this Euler method. I use the word Euler pronunciation. You can call it Euler's and so on, but the spelling is Euler. It's the name of the person, if not mistaken, Swiss mathematician, Switzerland mathematicians, well known. So we just want to know what is this method and then how it can solve what we call differential equation, basically first order, yeah. Okay, now we move on to second slide, fourth slide, sorry. This is a Euler method. So you want to know how to solve ODE, especially initial value problem. Yeah? Solve initial value problem, IVP. IVP, initial value problem for ODE by using Euler method. Okay. So why Euler methods? Or basically why numerical methods? Many of the differential equation of practical significance cannot be solved using the analytical method of calculus. So as I mentioned, the analytical method of calculus, okay, analytical method of calculus in your context, what you have studied past 5 weeks is about separable method. To solve the first order, we use a separable method, basically integration. That's why they say calculus. But our course is not calculus course. This is differential equation, the course, engineering maths 2. So the separable method, when you separate, after that you integrate, it's called analytical method. Now, the linear equation, first order dy dx plus pxy equals to qx is also analytical method. That is finding integrating factor and you find the output y. And then you solve Bernoulli. Bernoulli, you have to reduce to the linear equation. But in linear equation, you find the integrating factor. Same like non-exact equation. Non-exact equation, you reduce to exact equation. After that, you solve using integration, basically integration. So, thus, alternative methods are extremely important in all fields of engineering. So, you see, many problems cannot be solved, basically cannot be solved. So, therefore, we need an alternative method. So, the alternative method, one of them is Euler methods or Euler's method. This Euler's method is developed or designed or constructed or built from Taylor series. So this is important. Taylor series. Taylor series is the backbone for the Euler's method. Because without Taylor series, you don't have Euler method. So we are not going to study Taylor series. We just going to mention to you about Taylor series, just one equation. After that, we derive or we construct the Euler's method. It's very simple because we just considering the first order only. So Taylor series is a representation of function as an infinite sum of term that calculated from the values of function derivative at a single point. This is very important. At a single point. This is important. At a single point. So what is the meaning? We can represent a function in a series form. So this already discovered by the person named Taylor. It's the name of the person, Taylor. So we derive Euler's method from Taylor series. So how it works? Now you see the Taylor series. Yeah, see the slide. This is a very long series. That's why they call it infinite series. Infinite series. Yx, this is the output class. Yx equals to yx naught plus hy dash x naught plus h squared divided by 2 factorial y double dash x naught plus h cube over 3 factorial y triple dash x naught plus h power 4 factorial y power 4 x naught plus it goes to infinite. But for our study, we just take these two terms only, right hand side. The rest we just cut and throw away. We don't use this. So we make use of this, and then because you see here got dy dx, that's why we want to solve the differential equation. This is the differential equation, but this is the output. This is your output. So we make use of this part, and then we solve the dy dx, the first order only. Of course, this one all second order, third order, but we are not going to use all these things. So this one we cut out. So meaning to say they cut, cancel. So you only have 1, 2, 3 terms. Left hand side is the output. Right hand side is this one is the initial condition, and this is h y dash x naught. We will know the detail in the next slide. So now this chapter is to solve. It's about to solve the ODE. Which ODE? First order. This first order can be in the form of separable, linear, exact, non-exact. Also Bernoulli, first order. So any first order differential equation dy dx equals to fxy, you must write in this form. Dy dx on the left hand side. Anything, any term beside dy dx, you bring in right hand side. You form in this form. This is the standard form, the dy dx fxy. So if you want to use the Euler method, you must write first this form. Make sure you write the differential equation in this form. So as mentioned in the previous slide, by truncating the second derivative term, meaning you cancel all these things. If you cancel all these terms, this term, all you cancel it, then you will have what we call these two terms only. So that's why here you have this two term only, right hand side. So this chapter devoted to solve this dy dx equals fxy by truncating the second derivative term. That means no y double dash. So you only have yx approximately. You see this sign? This is approximately yx naught hy dash x naught. So this term dy dx equals to, you must substitute with this one, fx. So the fxy goes inside here, in fact. But we can calculate fxy at the point x naught, because this is initial condition, it will be given. So basically, you already knew this is your output, this is your input, we call it initial condition, this is given, and then this one you plug inside here. So h we will know, and this one also we know, so we can find the output easily. So that is the ideal class. So now the y dash, how do you calculate y dash x naught? Y dash x naught you calculate using this. Yes.
I can see any pointer.
You?
I can see any pointer.
Cannot see. Cannot see.
Yes.
What happened? Oh. Now can see?
No.
Also not.
Suddenly it became okay. Now?
No.
Oh, only the big one. The small one. Oh, you cannot see, huh? Sorry. Oh, cannot see this one. No?
No, sir.
No, sir.
I think they already blocked. What happened? Suddenly, not working class, yeah. Now can you see? Can you see now?
No.
This
No.
one? Now? Huh?
No, still cannot.
In the beginning, you can see.
No.
Cannot.
Since the beginning.
From the beginning cannot see.
Yeah.
Yeah. Cannot.
Huh?
Yes.
From the beginning, cannot.
Yes, sir.
I can see here. So how? I can see
But
here. Huh?
but we cannot see.
Yeah, we cannot see.
So how?
I don't know how.
That is the problem. I say I cannot. I can see. But the slide you can see. Hello? Hello?
Slide can. Pointer cannot.
Are you in my slide or outside? Are you in my slide? Are you in the slide number 7?
Yeah, we are. By truncating the second derivative terms, but we can't see a pointer.
Oh, can you read for me?
This one, dy dx equals to f bracket xy. Then by truncating the second derivative term, yx equals to yx0 plus hy prime x0.
Mm-hmm.
Yeah, that's all that now we can see.
Huh?
That's all that now we can see.
The pointer?
No, we don't see the pointer.
So how to do this? Are you in the slide number 7 now? Hello?
Yes, we are.
Maybe you should call the IT, sir.
Huh? Come again?
Maybe you should call the IT.
I can see here. That's why I'm putting the pointer here. Epic pen. Is that Epic pen? You know Epic pen?
No, sir.
So how now? I have no idea because I can put here. I can see here.
Sir, I think it's just the pointer we cannot see it, but we still can see the slide. So I think we better proceed with the lecture, I think.
Yeah. Okay. So
let's just proceed.
I'll try to solve in the next lecture. No? Huh? Okay. I try to solve in the next lecture. Is it okay with you? Hello?
Okay, sir.
Okay, sir.
So at the moment, I have no idea how to solve this problem. So in the next lecture, I try to work it out. Okay, so this one is the method. This is the method. So if you look at this equation, sorry, slide number 7, yeah. So y dash, this one. I can use this what we call, but this text is you cannot see. So it's very hard, yeah. So dy dx fxy, yx, this is the output, yx naught, hy dash x naught. So you must know this formula. You write down this formula. And now we move on to slide number 8. This is the method. Slide number 7 is just to give you how the second term was truncated, that means vanished. So you have only h y dash. Now, the Euler method it works like this. General equation for the Euler's method is yxi plus 1 equals to yxi plus hf xi yi. So where the step size h is b minus a, this one, yeah. Can you see it now? Can the highlighted one? Can you see, class?
Can, sir.
Okay. So h is b minus a over n, and this one, of course, this one does. Yeah, I highlighted. This one is yes. This is y xi plus 1 approximately equals to yxi plus h fxi yi, meaning the I, the small I, we have to change. We start with I0, and then I1, I2, I3, I4, and so on. So this equation actually is derived from the previous slide. If you look at slide 7, slide number 7, this one is general equation. Now, but general equation means just yx, just one value, but it's not one value. It is an iteration. You will have many outputs. That is the difference from chapter 1 to 3. So you have many different y output. So yxi plus 1 approximately equals to yxi plus hf xi yi. So this is your iterative equation. So the Euler method use iterative kind of finding the output. So you must understand what is the meaning of this equation. Yxi plus 1 equals to yxi plus hf xi yi with the step size h. So h equals to b minus a divided by n. What is b? What is a? What is n? So h is called step size. Yeah. So I highlight here step size. So b minus a over n. So what is b? What is a? What is n? So this b b minus a and b are the interval. This one. Close bracket, open bracket, close bracket. AB is the interval, and n is the number of interval. How many? We will show you later. Example, how we calculate this n and h. Of course, we want to calculate the h, provided b is given, a is given. B is the upper bound, a is the lower bound, and n is the number of interval. In particular, h also can be calculated this way, or defined as xi plus 1 minus xi. H equivalent to xi plus 1 minus xi. So, for example, you put I0, so x1 minus x0. That is your h. So, this method is also known as Cauchy-Euler method and point slope method. Why it is point slope method? Because of your dy dx. This part, the y dash x naught, because this is slope actually. You know, dy dx is the slope. It's a gradient. So that's why we call it as point slope method. Now, this figure on slide number 9, the predicted one and the true. So the y, actually, this is your output and your input is x. X is input, y is output. So what is happening here is you have your xi, this is the starting point. If I put I0, this is x0. If I put I0, this is x1. So the difference xi plus 1 minus xi is h. So this is your h. Okay, so what is happening here is this true value, is from analytical method. This figure just give you a rough idea what is happening in a numerical method, how it differ from the analytical method. So the true value, this is actually the output, the graph, y respect to x. The true value at this point, xi plus 1, is different from the predicted value. Predicted value is coming from the numerical method. So this predicted value coming from numerical method. You can write down. True value coming from analytical method. So therefore, there is a difference. You can see the difference. You see, this is different. So the height here is different. This height, the difference is called the error. So this error we have to calculate. But it's not easy. In order to calculate the error, you must know the true value. This is the problem. So without a true value, you cannot calculate the error. You just calculate the predicted one. So this is just to give you, and maybe in the near future, we can find some problems on how to find the error. Okay, so the error, of course, is a very big studies about the error analysis and so on. Okay, now this is example. So use Euler method numerically to solve this problem. Dy dx equals to 4x squared. At x equals to 2, from x1 to x2 with n equals to 1. Given y1, x1. So you have like this straight line. You put x1 here. Put a straight line. And you have a lower boundary x1 and then upper boundary x2. x1 to 2, that is the meaning. So x1 to 2, if you want to calculate, your a is 1, your b is 2, n is 1. So you substitute b minus a divided by n. So b is 2, a is 1, n is 1. This is given, class. So you are given, in this problem, we are given this information. This information is given. Given also this one. Only thing is you want to solve this equation at x equals to 2. We do not know what is your y when x is 2. That is what we want to find. But when x equals to 1, you already knew your output. When we say x naught. When x naught is 1, your y naught is 1. This we already knew. And this one we already knew. So your fxy is dy dx. This is 4x squared. You compare this one. You compare with this one. Yeah. So this is the equation. We're going to use this. So how do we calculate? Basically, all these are calculation. Yeah? So yxi plus 1. In fact, you must memorize this equation. Without this, we cannot do. We need this. Yxi plus 1 equals to yxi plus hfxiyi. So first, this formula you must know. And then this one is given. Sorry, this one is given. This one is given. What is the meaning? When x naught is 1, your y naught is 1. They don't write x naught, y1. You have to write. Now the step size, this is the step size. So step size, hb minus a divided by n. So your b, you see the calculation, yeah? B, your b is 2, your a is 1, and your n is 1. Given already. B is given, a is given, n is given. So 2 minus 1, 1. 1 divided by 1, 1. So your h is 1. That's why you have to calculate your h. Now this fxy also you have to calculate. Every time you must calculate this fxy. The reason is this value will change. This one is the initial x naught, initial y naught. So when x naught 1, y naught 1, right hand side 4x squared. So 4 multiply 1 squared, 4. So this is the value you have to substitute inside here. H already F. So H1, F114. So you have to write step by step, because otherwise we do not know how you calculated the value. So what the question says, you find y at 2. So I put x I0, this is my x1. So my x1 is 1 in this case. Sorry, x1 is 2. x0 is 1. x0 is 1. So we want to find x1. x0 is 1. So you want to find x1, the next x, which is x equals to 2, because that is the question. So equals to y2 equals to y1. This is x not 1, y1. So y1 is 1 given. H is 1. H is 1. F11. F11 you already calculated 4. You already calculated 4. So 4 multiply 1, 4. 4 plus 1, 5. So this is the answer. So y2 is 5. So you already answered, because they ask you to find y2. Go back to the question. What is your y? Because use Euler method to solve numerically, meaning numerically this one, you want to solve numerically at x equals to 2. So at x equals to 2, you must give the answer 5, sorry. So answer is 5. Now, what about y3? At y3. So if I write, can you see this class? Y. Can you see this class? Hello? Can you see this? Can you see this?
See what, sir?
Yes, sir.
Y3.
Cannot, sir.
Cannot
No,
see.
sir.
Huh? Y3.
Cannot.
Cannot see. So that means my pen is not working. So it's not what we call compatible with the PDF file. Yeah. So unfortunately, so is you cannot find, you cannot see. All right. So we just yeah. Now Y2. So Y2, this is how you calculate, yeah? Y2 equals to 5. So you already calculated, this is the calculation. So the answer is 5. Now, how do you calculate Y3? This is 2, N is 1. So you start with X1, X2. When X2, your output Y is 5. Okay, so you already found 5. Now, one more step, X3, write down. So at X equals to 3, that means X0 is 1, X1 is 2. Now X2 is 3. So Y3, you want to find Y3 equals to, this is, my I is 2. So I want to find Y3. So this one, my Yx2. So my Yx2 is 5, this 5. 5 plus, my H still 1, but F is 2, 5. Change this. This one class, F2, 5. So F2, 5 is equivalent to 4x squared. You must calculate 4x squared. 4 multiplied by x is 2, 2 squared. So 2 squared is 4. 4 multiplied 4, 16. 16 plus 5 is 21. So the answer is 21. So the y, write down here, the y3, I'm writing here, y3, at the point y3, the answer should be 21, like this. Can you calculate now, class? Mohammed Dennis. Mohammed Nur Hadi, Mohammed Afif, 1 Amir, Y3 cannot, sorry, why? Hello? Try. Y3 you should get 21. Can you calculate now? Use the formula Y3 equals to,
Yes, sir. We got 21.
yeah, answer is 21.
Yes. 5 plus 16, so you get 21.
Yes, you use the formula. 1 Amir. Are you 1 Amir? Muhammad Atif. Yeah, are you Muhammad Atif? Hello, please respond. 5 is 16. Yeah. 4 squared, 2 squared. Yeah. Yeah. 4x squared. 4x squared. Atif. 4x squared. X is 2. 2 squared is 4. 4 multiplied 4, 16. Yes. So the overall 5 plus 4 star. There is a star. So 4 squared, 4 squared, 4, 16, 5 plus 16 equals to 21. So this is the answer. Yeah, if you get 61, it's okay. Yeah, y1 is 5. Y0 is 1, y1 5, y2. Now we calculated y2 is 21. So can you calculate at just now at x equals to 3? So what is x? X equals to 4. So what is your y? So at x equals to 4, what is your y? So y, x0, x1, x2. So y at x equals 3, 21. So y 4 equals to yxi. Yxi can you calculate, class? Yeah, yxi. So x0, x1, x2, 21. So 21 plus h1 f x3, x3, 21. When x3, your y is 21. When x is 2, your y is 5. When your x is 1, your y is 1. So you have 21 plus 1, 4 x3 square. So 21 plus 36. So you should get 57. Yes. Yeah, very good. Yeah. Yes. Answer is Y4, 57. Yeah. You must get 57. Yes, this is what we call iteration class. This is called, even the word is not there. This is called iteration. So you find the next y using the previous xi and yi. So similarly, when x4, you get 57. Now you can create a table, make table x, y, x not 1, y not 1, 2-column table, x2, 2, x1, 2, y1, 5, x2, 3, 21, 4, 57. So you calculate. So you make a table, 2-column table. Make a table. Make a table. You make a table. You make a table now. You make a table, 2-column table. I do it now. 2-column. Two-column table. So in this 2-column table, first column, x input. 1, 2, 3, 4. Because your age is 1. You can see your age. When x1, y1. Write down here. When x2, y5. When x3, y21. When x4, y57. When x5, this is y4. When x5, so 57 plus h1, f3 21, f4 57. So 57 plus 1, 4x squared. 4 multiply 4 squared. 4 squared 16. So 57 plus 16 multiply 4, 64. So 57 multiply 64, what do you get? 1 to 1. So you should get 1 to 1. Can you get 1 to 1? Yes. So 1 to 1 is correct. So when x equals to 5, the y is 1 to 1, like this. So now you already have the table. So you see these values keep on increasing, ascending. So this is the problem with this method. So unfortunately, it's not converging. So you know, in solution of the differential equation, normally it should converge. But in this case, it is sort of diverging. So we look for more problems, how to use Euler method very effectively. What is the, how effective? We have to test. So in this case, you already found when x1, y1, x2, y5, x3, y21, x4, y57, x5, y121. So you can make the table. So this table will be very helpful. And then from there, you can plot the graph. You saw just now the graph. X is your input. Y is your output. So you can plot the graph and you can get whether the graph is linear or non-linear or curve. Then it can go to other type of what we call you derive, make a conclusion from the graph. So at the moment, for this method, we do up to the what we call the table. Okay. So from the table, we know the Y, how the Y, the behavior of the output. So the Y value is the output. Now this problem, maybe it looks simple because if you go back, this one can be solved by separable. This is the separable differential equation. Okay, you can compare. If you have time, you can solve this analytically because this is separable class. Dy dx equals 4x squared is separable, which you already studied in chapter 1. So what is new here is we are introducing to you Euler method. This is a new method. If you haven't studied, of course, this is new to you. So whether this Euler method can successfully solve this problem with very minimum error, as you saw the graph just now, the predicted one and the actual one, estimated one with the actual one, the true value comes from the analytical method. In this case, this problem can be solved by separable because dy 4x squared dx. So you integrate, you get 4 x cubed over 3. So y is 4 over 3 x cubed plus c. But the c, when x is 1, y is 1, so your c is 0. Sorry, when x is 1, y is 1, sorry, 1 equals to 4 over 3 plus c. So your c is 1 minus 4 over 3 minus 1 over 3. So your y is 4 over 3 x cubed minus 1 over 3. This is your answer. Write down, yeah? Your y is 4 over 3 x cubed minus 4 over 3. So if you substitute x1, your y is 1. So if you substitute x2, this is 8. 8 multiplied by 4. 32 over 3 minus 1 over 3, 31 over 3. when x is 2, 2 power 3, 8, right? 8 multiplied by 4, 32 over 3 minus 1 over 3. So 31, 3. So the answer is 10, 1 over 3. But you have 5 only. So we're too far. The error is very big. Almost 50%. So that's why the Euler method is not so accurate for this problem, right? Maybe for other problem, it may give you a good approximation. Okay. Any question, class, so far? Hello, any question?
No, sir.
Mohammed Dennis?
No question, sir.
No question. Mohammed Dennis. Mohammed Shalihin, yeah. Okay. So if no question, then we proceed to the second one. Use Euler method to solve this differential equation. You see, it's a very long one, but we try. But I cannot give you a full solution. I can go one step ahead. This one, use Euler's method to numerically solve dy dx. So you are finding the output y. Of course, this is separable, class. You can see this equation is a separable equation. This one is separable. This is separable equation. So you want to solve this from x0 to 4 with step size h0.5. The initial condition when x0, y1. So you are given already. When x0, y1. So you have to find the next one is x 0.5. And then after 0.5, x1. And then 1.5. 1.5, 2. 2.5, 3. 3.5, 4. So you got to do 8 times, class. 8 intervals. How do you know? You see, n is not given, h is given. Your a is 0, your b is 4. So use the formula h equivalent to, write down here, b minus a over n. So your b is 4 minus a is 0. 4 minus 0 divided by n equals to h is half. So you solve, you get n equals to 8. That is n. So that means you got to do n times. X naught is 0, y naught is 1. So when x is 0, your y naught is 1. Now the next one is, what is my y1? In this case, when my x1 is 0.5. So you want to calculate the y1. So when I put 0, this is x1. But this one is 0, this is 0, this is 0. So use this formula, to calculate the next y. So this one is x naught. X naught, y naught is 1. So your y naught is 1. Now we want to calculate y1, y2, like that. y3, y4, y5, y6, y7, y4, y5, y6, y7, y8, like that. So the first y is y0. So y0 is 1. This is the meaning. Y0 is 1, x0 is 0. So your h is 0.5. This one is already known. Now, this is your x0. That's why they write here 0. So x0, when x0, y is 1. So you are putting this inside here. This one is here. So you want to calculate this term, f x0, y0. You want to calculate x0, y0. You want to calculate f x0, y0. So f01 is minus 2x cubed. From where? From the problem, this one. You take this part. You put this as a fxy. H is 0.5. So this one, f xi yi, is your dy dx, this one. So you plug in the whole thing. x0, y1. So 0 plus 0 plus 0, 8.5. So 0, 1 is 8.5. So you substitute 8.5 here. So the next y at x 0.5, you want to calculate this. So y0, 1 plus h 0.5. This is your h. And f01 is 8.5. So 8.5 multiplied by 0.5 plus 1, you should get 5.25. Can you get 5.25 plus? Can you check that? So your y1 is 5.25. Can you get plus? Hello?
Yes, sir.
Got it. Oh, okay. So your y at x 0.5, y 0.5 is equivalent to 5.25. So we stick to our 2 decimal place. 5.25. Okay, so we already got that, right? Now you want to calculate, this is actually y1, yeah? Now we want to calculate y2. We want to calculate y2. That means y at x1. Two decimal numbers, but if you can go up to 3 is okay. So write down, yeah. So using Euler method, you want to calculate at x2. x2. So the calculation is y at x1, because this is x2, 1, equals to 5.25. Write down, yeah. 5.25 plus 0.5. So we want to calculate y at 1. So equals to 5.25 plus 0.5 f of 0.5, 5.25. This is the calculation. So 5.25 plus, write down here, 0.5, the f of 0.25. So you have to calculate now f of 0.5, 5.25. So you calculate this value. Okay, slowly, yeah. Press your calculator. Calculate f of 0.5, 5.25 equals to, you go back to the slide. So here, you must put here minus 2, 0.5 power 3 plus 12, 0.5 squared minus 20, 0.5 plus 8.5. Now simplify. Minus 2, 0.125 plus 12, 0.25 minus 10 plus 8.5. That will give you minus 0.25 plus 3 minus 10 plus 8.5. That will give you 1.25. So you will have 5.25. Use your calculator. 5.25 plus 0.5, 0.5 multiplied by 1.25 equals to, you calculate. So 5.25 plus 0.5 multiplied by 125. So you should be able to get 5.875. Can you verify this, class? This is at y x1. Yes, Najmuddin. Yes, sir. Yeah, the rest, when can? Muhammad Dennis. Muhammad Dennis.
Yes, sir, same. 5.875.
Yes, yes. 5.875. Yeah. Yeah. Muhammad Salman. Are you okay, Muhammad Salman? Muhammad Salman? Okay. All right. Now, how do you find this method? Yeah. Yeah. How do you find this method? So, anybody want to comment on this? Class, waiting for your answer. Hello? How do you find this Euler method? Mohammed Salman? Okay, so, hello? Can you hear me? Hello?
Yes, sir.
So can you find the answer? All of you?
Yes, we can.
5.875. All right. Can you calculate now at 1.5? You make a table now. Make a table. X, Y. When x0, y1. X 0.5, y 5.25. When x1, y 5.875. Now, can we do at x 1.5? One more round. So, at y at x 1.5. Can you calculate now? Najmuddin here. So 1.5. Y at 1.5 equals to what? Equals to 5.875 plus h 0.5 f of 1.5875. 3 decimal place. Can you calculate this, class? Hello? Please calculate now. So f of 1.5875, your x is 1. Okay, so your x is 1. Go back to the slide. So minus 2 x1. So minus 2 multiply 1 plus 12 multiply 1 squared multiply 20 plus 8.5. So you have minus 2 plus 12 minus 20 plus 8.5. So can you calculate that value? So minus 2 12 minus 20 plus 8.5 minus 2. You get minus 1.5. multiply by 0.5. Minus 0.75 plus 5.875. Answer is 5.125. So your answer is 5.125. Is that correct, class? F1. No, F1. F1, not 1.5. F1. So the answer is 5.125. Muhammad Salihin, yes. $1.5. What 5.125 is y at 1.5. Then you continue at x is 2. Sorry, x is x 1.5, 5.125, and x is 2. So y at x2 equals to 5.125 plus 0.5 f of 1.5, 5.125. So you can make table now. Y at 2. No, you cannot go y3 first. Y2. From 0, 0.5, 1, 155, and then 2. So if you calculate 5.125 plus 0.5 f 1.5 5125 is minus 2 x cube 1.5 power 3 plus 12 1.5 power 2 minus 20 1.5 plus 8.5. So 1.5 multiply 1.5 multiply 1.5. You get 3.375 multiplied by minus 2. Minus 2. You get minus 6.75 plus 1.5 multiply by 1.5, 2.25. Multiply by 12, you get 27. Minus 20, multiply by 1.5, you get 30. Plus 8.5. So 8.5 minus 30 plus 27 minus 6.75. You get minus 125 plus. Minus 1.25. So 5.125. 0.5 multiplied by 0.5. You get minus 0.625 plus 5.125. So you get 4.5. So you already got answer. Yes, 5. Very good, sir. Yes, 5 Aminuddin. Najmuddin. Yes. Any question, Najmuddin? So Y2, 4.5. So you can make a table now. First 2 column, first row XY, second row 0, 1, third row 0.5, 5.25, fourth row X1, 5.875 Y, fifth row 1.5, 5.125, sixth row X2, Y 4.5. So you do it 2.5, 3, 3.5 and 4. So 1, 2, 3, 4, 5, 6, 7, 8 iteration. So you continue as a homework. So now you don't give up. Continue with at home. Yeah. Continue with next is x at 2.5. So x 2.5 and then x equals to x equals to 3. And then x equals to 3.5. And then last one is x equals to, then you can stop. Yeah, any problem, class? Hello? Any questions so far?
No questions, doctor.
No question, huh? Very good. Muhammad Amir, yeah. Muhammad Amir, yeah.
Yeah, yeah.
All right, thank you very much. So continue with the x 2.5, x3, x 3.54. It is better for you to complete the table. The reason is you will keep on doing this for the next 5 or another 6 more weeks. So you make a table. The process is like iteration. So you create a table with 2 columns, and then the rows, first row x, y, second row x0, y1, third row x0.5, 5.25. Like that you complete until x equals to 4. Then you see the y output. You see just now the y suddenly dropped to 4.5. So we want to know what is going to happen, 2.5, 3, 3.4, 3.5 until 4. And then you do the analysis. You do the analysis. So you cannot stop at x just now 4.5. When x is 2, y is 4.5. And now we want to investigate what will happen when x is 2.5. This is very important because you can study the pattern of the output, where the values going to in the end. But the ending for this problem is we have to stop when x is 4. That is what we call the stopping criteria as per the problem. But it's not necessary you stop at 4. You can investigate further more if you want to. But I think it is sufficient because it's not easy to do manually, because you're doing by hand, using calculator, pressing, and then get the answers. So this is what we call time consuming. But reasonably, we can do about 5 to 6 iteration. 5 to 6 iteration. This is 8 iteration. Because if you stop and 3, 4 iteration, we do not know whether this value is correct or not. So we want to see whether this value gives a kind of convergent solution or not. That is another issue. For that, you got to study some more in detail. What we are currently trying to do is we try to find the output and make the table, and from the table we try to do some analysis. This means we need to stop at B. Yeah, x is B, x is A, y is B. Yes, sir. Yes. Parasha. Yes. That is the, after that, no need, because you asked to do from x0 to 4. So it's a very long process. 0 to 4, you have 8 iteration. So this is a very lengthy process. Yeah, any question? Why 2.5? Already got ready. Just now we found y2. This is 2.5. Yes, possible. But you said MMMZ, Mohammed Irfan. Mohammed Irfan said 4.5. Mohammed Shalhin said 4.75. Why this is different? Muhammad Irfan, careless mistake. Okay, no problem. Okay, take it easy. Practice. Take it easy. So, Muhammad Shalid. Muhammad Shalid. Is it 4.75? Anybody can verify the answer? At 2.5, Muhammad Shalihin. Y4, 7. Y2.5, Y2.5. Okay, can you fill up first? Y2.5. Y2.5, 4.75. So what is Y3? Can you answer Y3, please? 2.5. 2.5. Y2.5, 4.75. Is that correct, class? Okay, Y3, 5.875. So this is equivalent to Y1. Y2.5, 4.75. Okay. Y3.5. Y3.5, 7.125. And then Y4, you are saying 7. Y4 is 7. So if you see the solution is not stable, just like a bumpy kind of solution, because 5.25, 5.875, 5.125, then suddenly drop 4.75 and increase 4.75, and then 5.875, and then 7.125. So you can plot and then drop to 7. Yeah. So you already completed the table. Good. Shah Aiziam. Yeah. Y4, 7. Good. Okay. Y4, 7. Okay, so now you already completed the table. Very good. X from 0 to 4 with the step size 0.5. So if you analyze the table, when x0, y1, x0.5, 5.25, x1, 5.875, x1.5, 5.125, x2, 4.5, x2.5, y 4.75, x3, y 5.875, x3.5, y 7.125. When x4, y 7. You see these y values various. So we want to investigate what happened here. Why the y value is not consistent. So one of the reason is the step size plus h 0.5. This step size sometimes it's too big or too small. So we want to investigate. All clear? So we want to investigate why the solution is not consistent. So there are many reasons for that. One reason could be the method, but we already applied the method. So this is one of the numerical method. So there are other numerical methods available under numerical analysis. So the other reason is there is a possibility that your h is 0.5. So this 0.5, there are two possibilities, but increasing, decreasing the h. But it is very rare to get more accurate, more consistent output. You increase the h. This very rare, it never happened. So generally speaking, the best way to get more consistent output, you reduce the h. Now your h is 0.5. So you can try h 0.25, half of that. Because this 0.5 consider very large, big. So if you reduce half 0.25, then you may get some reasonably good output. But we cannot guarantee, we can try. If that doesn't work, then you can go for h 0.1. This is the smallest. But we cannot say this is the best. But from 0.5, you reduce to 0.25 and reduce to 0.1 and then see the y. Whether the y will give you a consistent result. Consistent means it should converge to one solution, unique solution. You cannot have a bumpy kind of solution. This is inconsistent. We say it, the stability of the solution is not good. So, therefore, you got to try many problems in order to come out with some kind of reasons for the improvement, how to improve. That is your further studies. So at the moment you make the table, you present your solution in the form of the table, and then you can also draw the graph if you want. See the behavior of the output, how the output behave. But it's all depend on the step size as well. Step size plays important role, and as well as the stopping criteria. It's a number of iteration from 0 to 4. So that's all for today. Any question, class? Any question, class? Very good. Okay. Please fill up your